This is Electric Universe, and today I was on Electric Cosmology Facebook page and someone posted the question, can someone explain this in simple terms in EU language? I would like to let folks know in other groups that there is an entirely different way to think about this. And the article was shared titled, Black Hole Sound Waves, Science Mission Directorate, posted to science.nasa.gov. So what I will do is narrate the article and then provide an answer. And the article was posted to NASA September 9th, 2003, titled Black Hole Sound Waves. Sound waves 57 octaves lower than middle C are rumbling away from a supermassive black hole in the Perseus cluster. The black hole resides in the Perseus cluster of galaxies located 250 million light-years from Earth. In 2002, astronomers obtained a deep Chandra observation that shows ripples in the gas filling the cluster. These ripples are evidence for sound waves that have traveled hundreds of thousands of light-years away from the cluster's central black hole. On the right of this image, the Perseus cluster of galaxies. Each fuzzy object is a galaxy, unseen in a vast cloud of hot gas filling the cluster. Near the center of it all lies a supermassive black hole. Earlier observations had revealed the prodigious amounts of light and heat created by black holes. Quote, "Now we have detected their sound too," says Andrew Fabian of the Institute of Astronomy in Cambridge, England, and the leader of the study. In musical terms, the pitch of the sound generated by the black hole translates into the note of B flat, but a human would have no chance of hearing this cosmic performance because the note is 57 octaves lower than middle C. For comparison, a typical piano contains only about 7 octaves. At a frequency over 1,000,000 billion times deeper than the limits of human hearing, this is the deepest note ever detected from an object in the universe. Quote, "The Perseus sound waves are much more than just an interesting form of black hole acoustics," says Steve Allen, also of the Institute of Astronomy and co-investigator in the research. Quote, "These sound waves may be the key in figuring out how galaxy clusters, the largest structures in the universe, grow." End quote. This image is titled, Peering into the Heart of the Perseus Cluster, left. The Chandra X-ray Observatory detected sound waves rippling through the gas on right. For years, astronomers have tried to understand why there is so much hot gas in galaxy clusters and so little cool gas. Hot gas glowing with X-rays ought to cool because X-rays carry away some of the gas's energy. Dense gas near the cluster's center where X-ray emission is brightest should cool the fastest. As the gas cools, says researchers, the pressure should drop, causing gas from further out to sink toward the center. Trillions of stars ought to be forming in these gaseous flows. Yet scant evidence has been found for flows of cool gas or for star formation. This forced astronomers to invent several different ways to explain how gas contained in clusters remained hot. None of them were satisfactory. Black hole sound waves, however, might do the trick. Previous Chandra observations of the Perseus cluster revealed two vast bubble-shaped cavities extending away from the central black hole. These cavities have been formed by jets of material pushing back the cluster gas. The jets, which are a counterintuitive side effect of the black hole gobbling matter in its vicinity, have long been suspected of heating the surrounding gas. But the exact mechanism was unknown. The sound waves, seen spreading out from the cavities in the recent Chandra observation, could provide this heating mechanism. A tremendous amount of energy is needed to generate the cavities, as much as the combined energy from 100 million supernovas. Much of this energy is carried by the sound waves and should dissipate in the cluster gas, keeping the gas warm and possibly preventing a cooling flow. If so, the B-flat pitch of the sound wave, 57 octaves below middle C, would have remained roughly constant for about 2.5 billion years. Perseus is the brightest cluster of galaxies and X-rays, and therefore was a perfect Chandra target for finding sound waves rippling through the hot cluster gas. Other clusters show X-ray cavities, and future Chandra observations may yet detect sound waves in those clusters too. So, on to the explanation. I replied, astrophysicist Dr. Gillian Belovry, with less than 6 minutes, explains the subject amazingly and concludes saying, quote, "The pitch of these sound waves is something like a B-flat, but 57 octaves below the middle C. And so, that's not something that we could hear with our ears because that's not within the range that our ears are able to detect." end quote. So with middle C at about 262 cycles per second, measured in hertz, you can find the frequency of the note an octave below by just having it. The C below middle C is 131, then 65, etc. You run into a problem pretty quickly. At only 8 octaves below middle C, you get about 1 hertz, which is 1 cycle per second. This is incredibly slow, and you could technically produce this note by just clapping every second. At this point, it's no longer really a note, and anyone who says so, probably a tuba, is just kidding themselves. At 57 octaves below middle C, you will have a note that is so low, not only is it not a note anymore, you have to wait several weeks between cycles. I'm not actually going to do the math that low, as I think you get the picture. The note is 262 hertz, halved 57 times, or about 1.818 femtohertz. That's 1 cycle every 550 trillion seconds, or 17.44 million years. That's a bit more than 0.1% of the, quote, age of the universe. An unfathomably long time. Notes are an intuitive way of explaining the concept. A note is just a vibration. To a physicist, the units match up. The EU explanation: dark discharge, or dark current mode. There's no such thing as a black hole. The regime between A and E on the voltage current characteristic is termed a dark discharge because, except for corona discharges and the breakdown itself, the discharge remains invisible to the eye. A through B. During the background ionization stage of the process, the electric field applied along the axis of the discharge tube sweeps out the ions and electrons created by ionization from background radiation. Background radiation from cosmic rays, radioactive minerals, or other sources produces a constant and measurable degree of ionization in air at atmospheric pressure. The ions and electrons migrate to the electrodes in the applied electric field, producing a weak electric current. Increasing voltage sweeps out an increasing fraction of these ions and electrons. B through C. If the voltage between the electrodes is increased far enough, eventually all the available electrons and ions are swept away and the current saturates. In the saturation region, the current remains constant while the voltage is increased. This current depends linearly on the radiation source strength, a regime useful in some radiation counters. Dark regions of glow discharge. A glow discharge in a cylindrical tube, shown in black and white. Dark regions are in black, and visible regions are in white. C through E. If the voltage across the low-pressure discharge tube is increased beyond point C, the current will rise exponentially. The electric field is now high enough so the electrons initially present in the gas can acquire enough energy before reaching the anode to ionize a neutral atom. As the electric field becomes even stronger, the secondary electron may also ionize another neutral atom, leading to an avalanche of electron and ion production. The region of exponentially increasing current is called the Townsend discharge. D through E. Corona discharges occur in Townsend dark discharges in regions of high electric field near sharp points, edges, or wires in gases prior to electrical breakdown. If the coronal currents are high enough, corona discharges can be technically, quote, glow discharges, visible to the eye. For low currents, the entire corona is dark, as appropriate for the dark discharges. Related phenomena include the silent electrical discharge, an inaudible form of filamentary discharge, and the brush discharge, a luminous discharge in a non-uniform electric field where many corona discharges are active at the same time and form streamers through the gas. E. Electric breakdown occurs in Townsend regime with the addition of secondary electrons emitted from the cathode due to ion or photon impact. At the breakdown or sparking potential VB, the current might increase by a factor of 104 to 108 and is usually limited only by the internal resistance of the power supply connected between the plates. If the internal resistance of the power supply is very high, the discharge tube cannot draw enough current to break down the gas, and the tube will remain in the corona regime with small corona points or brush discharges being evident on the electrodes. If the internal resistance of the power supply is relatively low, then the gas will break down at the voltage VB and move into the normal glow discharge regime. The breakdown voltage for a particular gas and electrode material depends on the product of the pressure and the distance between the electrodes, PD, as expressed in Paschen's law, established in 1889. So I'll conclude this video with that modern science exclaims black holes are just empty space, gobbling up matter. The electric universe theory has an answer, and it's based off of empirical evidence here on Earth. Anyone can recreate dark discharge in a vacuum tube to see what you cannot see with your own eyes.